Unfortunately for poor Professor Tim Atkinson, he's got to follow that. Tim, Professor at UCL, will outline some of the achievements of British cave science at home and around the world. So without further ado, we will race on. Tim.
Thank you. This is the calm bit. Actually, I'm not going to say very much about the science of caves. There's a lot of science in studying caves, in working out how they form and so forth. I'm not going to talk about that because what I really want to do for this audience is to indicate why speleology is something to take seriously. It's not just a recreation. It's not just a lot of clever young people going, rich young people going off to far parts of the world and exploring things. It has wider implications and wider reverberations than that. And I'm going to concentrate largely on the influence that it's had on geographical sciences, because that's how I've spent most of my life. So this isn't going to be autobiographical, but it will touch. Some of my examples will touch on things I've done, others will be from other people. So, if we advance the first slide, I sometimes think of this as being a bit like a braided river. So there's, at the bottom here, some speleology here. Here's the channel of speleology advancing as we go through time. And here are some of the other geographical sciences, which Andy mentioned at the beginning. And from time to time, they cross, like in a braided river. And of course, as in a braided river, there's a sort of mixing and an influence and a fertilization. So I'm only going to talk about three things. In fact, it might be two if I can't talk as fast as Tony. I'm going to say something about where does the water go. This is a question cavers ask a lot. You know, where does this river or underground stream come out? I think caving has been the trigger, although not the sole trigger, for a radical revision of what we think of as the time scale of landscapes, how long it takes landscapes, not just caves, but landscapes over the top of them to form. And I'll finish by saying something about the mapping of past climates using stalagmites, which has become a major element in climate science, paleoclimate science. Well, what is it that distinguishes speleology and caving? And I mean caving, I don't mean just the scientific cavers, but I mean the culture of caving. What it's distinguished by is this: cavers make maps. It's an intrinsic part of caving, and somebody who spoke towards the end of this 2-day epic, or 2.5-day epic of lectures that Andy told you about at the very beginning, said on a video of original exploration in Spain, I think, how are you getting on? Because if you don't, it doesn't exist if it's not on the survey. In other words, they were, in that case, surveying compass and tape and clinometer and so on as they went along into this never-before-seen cave passage. So that's a bit unusual. Usually you explore it first and come back and survey it a bit later. But the culture of making maps is absolutely intrinsic to caving, not just to speleology. In fact, it's the foundation of speleology. So I don't think I'm being too fanciful here, particularly for this audience, in showing Mercator's map of the Southeast Asia here, that's 1603. That bears the same relationship to modern geographical science as Cavers' maps do to speleology and its influence on geographical science today. So it's something I think we have to take quite seriously. This is a map of the Mulu caves that Tony spoke about. So there's about 360 kilometers of cave here in Sarawak in Southeast Asia, all of it explored since the Royal Geographical sponsored Society in 1970, Royal Geographical Society sponsored expedition in 1978. Okay, surveying. This is one of my mentors, actually. This is somebody whose name you probably won't know, called William Stanton. He's better known in the geological world, but even then his name doesn't reverberate down the aisles, but he was an exceptional cave surveyor. And here he is in action in the 1950s. I met him when I was a schoolboy in the 1960s, around the time that this map was published. This is a map of Swildon's Hole in the Mendits, I'm sorry, I pressed the wrong button there. Up here you've got the plan. Notice the grid, which you can relate to the national grid. Here we see the cave in relation to features overhead. A long section, extended section, so you're looking at it from the side here. A proper three-dimensional map, even at that time. Nowadays it's much easier to do this sort of thing, to present this sort of thing on a screen and rotate the map, and you can see the cave in 3D. But this actually set new standards for cave surveying, and cave surveying has become quite a high precision business since then. Not high in the sense of engineering standards of precision, but certainly good enough to relate to surface features and to put the cave in its geological context. So this is actually a slightly more updated version of that map and simplified to illustrate a scientific paper on invertebrates in caves, cave fauna. The key thing here is that the cave has a big stream going through it. And this brings me on to the first of my three topics, my question of where does the water go. So over about a century of exploration, we're looking at the kind of situation of what's known in the cave round about, I would say round about 1995 or so, maybe 2000. This was the entrance up here. The stream disappears underground, and you can follow it through this long passage, about 1 kilometre or more of passage. The S's refer to places where divers have had to explore, and these are sumps, as Tony showed you. Finally, here at sump 12, that's the limit of exploration, and funnily enough, that's been the limit for about the last 50 years. So the question is, where does the water go? Well, how can you find out? Here are people trying to follow the water. Here's one of those sumps on the right, waterfall near the entrance on the left. Well, one way which you can try to follow the water is to put something in it and then look to see where that something comes out, perhaps in springs nearby or further away. So this is a technique which a few older people in the audience might recognise this chap. This is David Ingle-Smith, who's now in Australia, but was very much a prominent geographer in Britain in the 60s and 70s. And under his tutelage, several of us started to develop this water tracing method where we used the spores of a club moss called Lycopodium. And here they are. They're about 30 microns across, and they're buoyant in water. They don't actually float, but they're carried along in the turbulence of water. They're just about neutral buoyancy. And they're quite small, so they don't get filtered out. Here is Dingle putting some spores into a stream sink in Yorkshire, and here he is holding one of the plankton nets which would have sat in the stream behind him. That's coming from a spring and would filter the water. We take the sediment out of that net and rather laboriously look at it under a microscope and see whether it had any of our dyed spores in it. And in that way we were able to trace Swilden's Hole, the cave I showed you before with the survey, down to the very well-known cave at Wookie Hole, which I'm sure nearly everybody in the room knows about. A large show cave open to the public, rather garishly lit and illustrated, but a very significant karstic cave, and significant for a number of reasons. One of them is that it's the birthplace of cave diving in the world. The first cave diving was conducted here in the 1930s, and this shows a long section through Wookie Hole. So this is the plan here. The entrance is down here. The public originally could visit this bit, and then divers explored up to about here. The public, some 30 years ago, were able to visit this part because a tunnel was dug through here. Some very nice underwater surveying to make sure that they were in the right place. I think a surface entrance was also opened up here somewhere. Divers have pressed forward and forward and forward and forward. But they haven't just pressed forward. You notice that in the section here, they've pressed downwards. And this shows something which really couldn't be found with the water tracer. The Lycopodium could not possibly have told us that the conduit here goes down. The explored depth is 90 meters. It may go deeper. It's It's busy kind of looping up and down at the bottom here, and obviously this is a very, very difficult thing to explore indeed. It's not part of my brief to talk about the difficulty of underwater exploration, but there have been some pretty remarkable things done. So if we broaden that out, here is Swilden's Hole. Here's the water tracing line that connects it to Wookie Hole here. Lots of other sinking streams and cave streams draining to various different springs around the Mendip Hills. So the light colour here is the limestone. This is the limestone plateau. Tony showed you this system at Cheddar Gorge. That's the Cheddar Springs. And this is a very important map. This comes off the British Geological Survey website, but this map was created by speleologists, by cavers, mostly by slightly academic cavers, but cavers nevertheless. They were cavers first, and then they became hydrogeologists, or whatever you want to call them. And why is it important? Well, the first reason it's important is that all these springs along the top here, plus the Cheddar Spring, are the water supply for a city of 1.5 million people, Bristol. So this map shows the drainage area that has to be regulated. The activities there have to be regulated in order to protect the water supply of Bristol. And it also shows you how vulnerable the water supply of Bristol is, because the tracing tests show that it's only a matter of hours or days for some of these waters to flow through. Less than a day in flood for water to go from here to here. Less than a day in flood for water to go from Swilden's Hole to Wookie. But up to 10 days or 3 weeks, still very short, during periods of low flow. But nevertheless, this is the kind of system which requires, it doesn't filter the water well, and it requires regulation of activity in this area. And the way we regulate activity is through an agency called the Environment Agency, and it's groundwater regulations. Now, there are other ways of following water. For example, instead of adding those particulate spores, you can add a fluorescent dye. So this is a red fluorescent dye, which is going actually into a karstic sinkhole in the Lincolnshire limestone, one of these Jurassic limestones that are rather disappointing for cavers. They don't have many caves in them. They have a few, but not very many. And one of the advantages of that is that you can measure the concentration of your tracer in the water using an instrument like this, which is being deployed in the field back in the 1970s, powered by a generator here, and it's monitoring these springs behind. You can also take water samples. This is one of my former research students taking a water sample from a well. And when you do find your tracer, you can plot against time here, you can plot the concentration of the tracer. So this is something which is known as a breakthrough curve and shows the concentration of the tracer arriving here, rising to a peak, and then forming a descending tail. And this is very, very useful. I don't have time to go into all the uses of this, but one of the things you can do, you'll see in a moment, if you have a breakthrough curve, you can use it to model the behavior of contaminants that might be accidentally spilled into the sinkhole where you put the tracer, or into some other part of the aquifer. Now, I want to just say a very brief bit about two cases, and I'm moving right away from the cavernous parts of Britain and into Britain's biggest karst area, which is actually on the chalk. And the chalk is very important, particularly to Londoners, of whom there must be a great number in the audience. The chalk is extremely important because it supplies about 2/3 of your water, your drinking water. And this is the M1 and the M25. At the time the M25 was opened, you'll all, probably everybody in the room will at some time or other have experienced this intersection, multi-level intersection. This is just at the end of construction. And here the road is going to be drained. All these, I forget what you call them now, these subsidiary roads, and the M25 itself, they're all drained into soakways in the chalk here. This is a very low point. It's below the natural level of the landscape. At a very late stage in construction, somebody had the bright idea, and it wasn't me, of pointing out that the groundwater might flow rather rapidly from there, and that there was quite a risk that there might be a spillage from a tanker, here's a tanker, into these soakaways. And what would happen if that occurred? Well, we put a tracer in to find out. And so on this map, here are the soakaways. And this is the place where the water supply from Watford and St Albans is extracted from the chalk in a big pumping station. And the tracer went there in 3 days. There's one of the tracers. That's actually a bacteriophage, Hazel. So the first arrival was after 3 days. So the tracer was travelling at 1 kilometre a day, and poses a serious, the soakaways pose a serious risk to the water supply. So they couldn't alter the road, but they have what they call special procedures for emergency services in place, which will protect the inhabitants of Watford and St Albans in the event of a tanker spillage of miscible materials. This is an earlier study which I did with Dingle Smith, actually, back in the early 1970s. This is the water supply for Portsmouth. Here's Portsmouth down here. Here are some big springs. And down here today comes the A3M, which was in the planning stage in the early 1970s. And it was proposed by the road engineers to build a big soakaway just here. And the Portsmouth Water Company didn't like that idea at all. And they asked Dingle and I to do a tracer test, which we did. And we showed that the water went from the proposed soakaway to the springs, again, in a matter of 3 days, just over 3 days. And this time we've got a breakthrough curve like this with the dye, and we were able to scale that up because we'd measured the concentrations. And we said, let's pretend a 20-ton tanker of methanol has spilled here. That would send the inhabitants of Portsmouth blind, drunk, for 5 days. So as a result, the road was re-engineered. It wasn't built for another 20 years, but when it was built, it was completely re-engineered as regards the drainage. So you see that speleology indirectly is having quite an impact on things that you might think that it has no impact on at all. This is the end of that story, and I'm not going to go into it in detail, but the Portsmouth Water Company and the Environment Agency have done a lot more tracing to this site, and these are groundwater protection zones in which different activities are regulated. I hope that they're based on the right groundwater model. They're not based on tracer tests. They're based on a more, well, in some ways conservative, in some ways alarming model, because the model suggests it'll take 400 days for tracer to get from here to here. But I wonder whether that's really right, because this is the traced part, and you see it only takes a few days for half the distance. And this is quite topical. This is a proposed shale gas site here. So there's a potential, though not definite, source of contamination here if anything goes wrong with, if the shale gas drilling goes ahead, which it may not, and if anything went wrong with it. So let's hope that the Environment Agency has this right. All right, now I want to move on now to my second topic, and that's about time in geomorphology. So here we are. This is one of Tony's photos of one of the Yorkshire caves, and it's quite nice because it illustrates the theme, as you can see. And I'm only going to take a single example. But Tony alluded to this in his talk. You might have missed it, but he did allude to it when he talked about Derek Ford. He mentioned the caver from Bath who went to Canada and founded a laboratory for measuring the age of cave deposits. Well, from Derek Ford's work, which we'll see more of in a moment, has come an enormous lengthening of what we conceive of as the time span for the formation of landscape. Because with this mapping, you can relate caves underneath the ground to the landscape evolution above them. Now let me show you one example, which is from America. It's nothing to do with Britain, but it happens to be quite clear, so I can explain it, and I hope you'll see the point relatively quickly, because we don't have very much time. Andy, I'm hoping you're going to give me another really little less time as that. Goodness me. Let's move on quickly. I'm going to take the example of the Grand Canyon here. So uranium lead dating has been applied to cave deposits in the side of the Grand Canyon at about 10 sites. And these are all at different heights above the canyon floor. So those are the sites, and later on we'll see a cross-section along that red line there. So these are the sorts of deposits up in the left here which have been dated. These are actually coatings on the wall of the cave. They're not your conventional stalactites and stalagmites, and they form underwater. They've actually formed when the cave was filled with water and it was below the water table. So these, when they were deposited, were below the level of the river in the Grand Canyon, the Colorado River. So if you measure their age, you're getting an estimate of the time that it's taken for the river to cut down from the elevation of the stalagmite or of the deposit to the present elevation. Here are some people at the water table, you see. They're wading across the water table where it comes out in the river. And here is the technical stuff to do with dating, using uranium decaying to its ultimate daughter, 206 lead. And this has a very long time scale. You can measure the age of the Earth with it, but technical advances had to be made before you could measure things that were as young as about 1 million years. Those advances were made about 15, 20 years ago, and these are results from about 10 years ago, or a bit less, from an American group who measured the age of these water table speleothems. And you see they're getting ages in the range from less than 1 million years to about 17 million years here. And I'm going to concentrate on this one now. So here's the Grand Canyon. Here's the cross-section that I promised to show you. That's Site 4. That's the speleothem that's 17 million years old. That's the level of the Colorado River at the time that speleothem was deposited. And of course, the Colorado River is now down here. So that is the amount of incision that's taken place by the Colorado during that lapse of time, 17 million years approximately. So if you do that for all the speleothems, you get an incision rate. The incision rate is the amount of incision divided by the time elapsed. And this is a plot of incision rate as a function of distance down the Colorado. So you're coming down from the upper part of the canyon down to the western part of the canyon, the lower part. And you see that here we've got a variety of incision rates, but they're all high relative to the western part. So in the west, the incision rate is down here. It's about less than 100 meters per million years. And here it's more like 300 meters per million years, possibly even higher in one or two places. So here's the Grand Canyon as first illustrated in the geological literature. And if you notice the plateau up here, if you take the formula age and canyon depth against this, divided by incision rate, then we can estimate the age of the plateau. It's about 20 million years in the west, 6 million years in the east. And this represents an enormous lengthening of the geomorphological timescale. And that has come from caving. And I think this is the last thing I'll have a chance to say, so I won't talk about stalagmites and climate. But here we have lots of different dating methods here. And this is a book to show you how the change has taken place. This is a book published in 1977. And this is on geomorphology and time. And as far as radiometric dating was concerned, the timescale came from radiocarbon, and it was a 20th of a million years. So the timescale is now 400 times longer in the Grand Canyon example than was conceived in this book by very respectable geomorphologists at that time. It's because the methods simply weren't there. And this is Derek Ford, whom both Tony mentioned, one of our greater exports from Britain to Canada, and he broke this radiocarbon timescale by using uranium to date speleothems. And I just want to finish, really, by pointing out the timescale for some of our local landscapes. So the Mendip Hills Plateau, if we use this same methodology to extrapolate back, we think that the plateau there might have been exposed and formed about 3.5 million years ago. The same for the Peak District upland surface, mapped by Keith Clayton. that would be about the same age. And in the Yorkshire Dales, Tony here, Tony Waltham, who is not just a caver, not just a fantastically rapid speaker, but also a pretty mean geologist, he has used stalagmite dates to estimate the exposure date rather than the plateau date of the Yorkshire Dales limestones around 1 million years ago. And this is one of the places it all began. This is a letter in 1975. I've stolen this from Tony. This is a letter from one of Derek Ford's research students, Russ Harmon, quite a noted American geologist now, reporting the very first Quaternary dates in Britain that were older than radiocarbon could go, and they're about last interglacial, about 100,000 years old. That led very quickly to a paper with Tony and Pete Smart and Russ Harmon and also myself. And you see what's happening here? These are the publications in the geologic and geographical literature on dating of karst landscapes and dating of stalagmites for climatic purposes. They're now running at about 130 a year, whereas before 1975 there was nothing. And I'll finish there. Thank you very much.